As you know, we are going to talk about celestial navigation today. We did a kind of presentation last year. Some of you were here. So this year, we decided to divide it in 3 days. Okay, it's going to be today, tomorrow, and Thursday. Okay, and the reason why we separated in 3 days is because today we are going to do the theory. Okay, just for you to understand, what celestial navigation is about, and the main theory behind. Very simple, okay, you don't have to be a mathematician or a magician or anything like that, okay, so you will learn it. Tomorrow, if everything goes well, we go outside and we're going to take the sights, okay, with the sextant and everything, and then on Thursday, we're going to come back here to the classroom, and we're going to do a math, okay, to calculate the latitude and longitude, and hopefully we're going to be somewhere in the Keys, okay, hopefully, Yeah, might be in Cuba, might be in Cancun, but, there's a margin of error, okay, so, but it's just to lower your expectations, all right? Okay. Well, in terms of the logistics, if anyone wants to move up, that's fine. As we said, we don't charge. There's a couple of free seats over here. If someone cannot hear me well or cannot see from back there, there are a couple of seats over there. There's one seat here. Anyone can move, same price. Okay, we don't charge extra. It's not like American Airlines that you move forward, you need to pay more. No, nothing. You move forward, same price. Don't worry for that. No service here, no beverage service, nothing, okay, so sorry for that, all right? And the emergency exits, you know what they are, like here, like two in the back, okay, and I wouldn't go that way just in case, all right? Okay, all right. The last thing is, all right, so while everyone accommodated, the last thing is, the presentation is not, it's going to be like a free presentation, then we share it. Anyone who wants the presentation, we share it later. Okay, when we finish, it's just a PowerPoint, okay, so nothing special than that, all right? If anyone has a question, please stop me at any time and ask, okay? So my English is not the best in the world, as you can see. My accent is even worse, okay? But my Argentinian accent, from Buenos Aires, but I do what I can, okay? So I've been in this country for 25 years, and, when my kids, when I talk English, my kids, Dad, after 28 years, you learn nothing of English. You're a disaster and everything, but I accept it, that's fine, I accept it, don't worry. All right, so but anyway, seriously, if you have any question, please stop me. The idea is that, you understand what we're doing, okay? Ask all the questions you want. And at the end, and the best part of everything is that at the end of the presentation, day 3, it's not going to be an exam, okay? So you are not going to get an A, a Z, or anything like that, okay? Don't worry for that, okay? So you don't have to get stressed and study and do anything, right? Okay, is that fine? Yep. Yeah, are we ready? All right, so my producer told me that I had to stay on this side, okay? So on this side on the screen. So I'll try to stay on this side. I brought this, the latest technology, okay, that was able from Apple, okay? But trust me that it works, okay? But it looks like a rod, right? A stick, right? Which it is, of course. But this is part of something that we are going to do together tomorrow outside to get, to get this noon side. This actually go by this. And then we're going to take, using by this, I explain to you what I'm going to do, but this is, we put it on the ground like this, and with this we put it like a north-south, okay, with the compass, and then we're going to, one of the things I'm going to see, or when I check tomorrow is this, okay? So it looks like a stick, it is a stick, but it's part of like a little more complex, scientific instrument, put it that way, okay? So, okay, you can get, say it again? What do you call it? No, the stick, no, the only thing that we're going to do, I'll explain later, but the only thing we're going to do with this is, we are going to put it on the ground, at noontime, the shadow or the shade will project north-south, and that's the time we're going to take a side, okay? So, because one of the things that we need to know, and explain later, but we need to know when the sun crosses exactly north-south position. So one way is to measure it, second way is to measure this, the shade or the shadow of this, and put it like this, okay? Yeah, very simple, but trust me that it works, okay? Just go to... So we can name it the two-stick method. Yeah. No, I call it the survival method, but no. And you can use this anywhere in the world, at home, wherever you want. The only thing has to be on the ground, right? You can't do it on the boat, right? There has to be something that is fixed, okay? But anyway, we'll talk more about this. I bought this, you bought to Michael's or Hobby Lobby, one of those places, for $3, you get it, okay? So no more than that. But anyway, for now, it's going to be like the old-fashioned pointer, okay? All right, well, let's get started, okay? Well, we are in the winning part, so we don't know that part. Neil already did like a little introduction on myself, okay? I don't want to talk too much about myself, but I was born in Argentina almost 60 years ago, and I've been living in the US here for 30 years now. And what I do for living, which is not this, but I mean, what I do for living is, I mean, I'm in the export-import business, so we export food and cosmetics and health and beauty products from Miami to the Caribbean, Central America, South America. That's what I've been doing for living for 30 years now. And then, you know, when I have some time, I do a couple more things, okay? So what I want to show you here is what I don't do for living, okay? So let me see, it works. It should. Hold on. Okay, sorry. Give me a second. Well, it was working before, eh? Hold on. No, I had to move I had to move the mouse on this side. Okay, back again. So, well, you know my name, Martin Caminos. One of the things that I am is I'm a commercial pilot, okay? So I don't fly commercially, so I fly just for fun, okay? But that's one of the things that I do over the weekend here in South Florida. So my base is the Miami Airport. It's now called the Miami Executive Airport. So from there, over the weekends, not every weekend, but I mean, from time to time I fly. Sometimes I go to the Key, I go to Key Largo, to go Marathon, go to Orlando, you know, just like a fly for fun. The other thing that I do, I'm a sailing instructor as well. I'm part of the Coconut Grove's sailing club in the Miami area. So I go sailing over the weekends as well. I'm a sailing instructor as well, you know, whenever I have time. The only thing that I'm celestial navigation instructor, by the way, okay, as well. I mean, and these two parts, I mean, these two, I mean, are like titles, let's say, or certification that you get from US Sailing, which is the US Sailing Association, right? Which is like kind of the NBA or an NFL of sailing, okay? So that's the institute what it is. And what else? The last part is I'm a radio amateur as well, okay? So from time to time I have my radio antennas and everything. I brought some equipment here that I do during the day. So these are all the things that I know that I do that are not for living, of course, right? So these are all expenses, as you can imagine, right? So, but anyway, that's pretty much what I do. But anyway, I don't want to bother with this one. Let's go with this one, okay? Let's see how it works. But let's talk a little bit about the agenda, okay? So we want to talk a little bit about what celestial navigation is, okay? So you can understand what it is. We're going to talk a little bit about the celestial body coordinates, which are a little different than the coordinates that we use in astronomy. One of them is similar, you see the other one is a little different. At the end of the day, they are the same, okay? They are just different points of reference, okay? That's pretty much what it is. Then we talk about the noon side. Noon side means that we want to take the side with the sextant tomorrow at noon. At noon, when I mean at noon, it's not at 12, right? It's when the sun crosses what will be the north-south line, okay? So that's the noon, that's the solar noon, okay? Not the 12 here on the clock, okay? That's the solar noon, and that's why we need this part too, okay? But we don't want to talk about later. Well, we want to use the sextant in practice, okay? This is a little piece of equipment here, that's a sextant, okay? Then we talk a little bit about this, but don't be impressed by this, okay? So this is just a protractor, okay? The only thing that it does is to measure angles, okay? It looks like very sophisticated, very intimidating, but the only thing that it does, again, is just a protractor, okay? The only thing we want to do is to measure the angle between the sun or whatever body, like we want to measure this angle, right? So between the horizon and whatever body, right? The sun, the moon, or the stars, or whatever you want to measure, okay? So that's the only thing it does, okay? To measure this angle, okay? It's a protractor, okay? It's a little more sophisticated, but at the end of the day, that's the only thing it does, all right? What else? And then if everything goes well, I mean, tomorrow we'll take the sites over here, right over there, where the PR is in that area. And if everything goes well, we come back to the classrooms on Thursday and we calculate the latitude and the longitude, okay? That's what we'll do, okay? So today is going to be just theory, a couple of charts just for you to understand. And tomorrow we go and have some fun and doing the sites, all right? So far so good. Any question, right? No? Are we okay? Right? Okay. So what is celestial navigation? Well, it's very easy, right? It's just a technique to be able to calculate anywhere on the Earth, I mean, your position, which is latitude and longitude, okay? That's what we want to do, okay? Well, nowadays we had the GPS and the Google Earth and everything, but before that, which is 30 years ago, I mean, it's not antique history, right? We're talking about the 1980s or 1990s, you know, and before. The only way to get your position on the Earth was pretty much celestial navigation, okay? And it's still used, okay? There's not, I mean, antique history, trust me, okay? So as I said, I mean, celestial navigation started probably 2,000 years ago, right? No, it's not something really new. It's something that the Egyptians, the Phoenicians, the Greeks, and all the people, even the Arabs, okay? All the people in that region, in the Mediterranean, they knew the basic techniques and they knew how to do it, okay? So it's nothing really new, okay? I mean, then it got more refined with time, with better instruments and waiting timepieces like this. But I mean, the technique and the basics have been known for 2,000 years, okay? What else? Celestial navigation can be practiced on land, water, on the air, okay? So here we practice on land, but you can practice, of course, on a boat, sailing, or you can practice on a plane, right? No, on American Airlines plane, because you need to see, pretty much, I mean, the sky, right? So you won't be able to do it out of the screen of the American Airlines plane, but the old planes have like a domo like this one, which is like a kind of like a transparent glass domo, and they used to do it that way, okay? And again, this was on the air was done until the 1960s, 70s, okay? The first Boeing 747, the big one, the jumbos, and even the 707 has like a sextant like this one, okay? And they used to do it, okay? So then they came GPS and other inertial system to navigate, so celestial navigation for them was kind of antique. But on the water, I mean, it's still used, right? So if you take like a cruise ship or any commercial vessel that takes the container, I mean, they're still using as a backup, okay? The first use what is called inertial systems, then they use the GPS, and the third, the backup, is this one, okay? The celestial navigation, okay? So it's still used, okay? It's not used as a primary source of navigation, but it's still used, okay? So don't think that, I mean, it's like antique history, okay? They still use it, okay? And captains and everything that any captain on a commercial vessel or on a cruise ship, I mean, they need to know how to do this, okay? That's a requirement, okay? They might not use it all day, but it's a backup, okay? Okay, what else? As I say, it's still used. And what else? That's probably one of the things question, okay? So what is the expected precision of this? It's like a 2 miles radius, okay? So we think, I mean, if everything goes well and in practice, I mean, it should be 2 miles radius from where you are, okay? I mean, sometimes it's less. I mean, sometimes you can do it 1 mile, sometimes with 3, 4, depending on the day, depending on, the weather. I mean, it's not the same to take sights, from the ocean here on the land that you have all the time down for a ship that is moving like this, and it's a little more difficult. And sometimes it's cloudy, sometimes you get the reflection of the sun over the ocean, so it's very difficult to see. So anyway, so let's say, I mean, just to be honest, it's going to be probably 2 miles, depending on kind of section you have as well, but 2 miles is fine. So question to the group, I mean, do you think 2 miles is good, bad, it's a disaster? I mean, what do you think about 2 miles?
It's searchable.
Is what?
It's searchable.
It's searchable. All right. Okay. If you compare it to the current GPS and everything, what is the precision of the GPS? Any idea, more or less? I guess. How much? A few feet, right? Maybe 10, maybe 3 feet, 5 feet. Yeah, it depends on what GPS you use, right? If you are the military, probably like 1 feet or less. And for us, regular mortals, it's probably around like a 3 feet or 5 feet or whatever, right? So 1 meter or so, right? Okay. So the thing is, when you compare 2 miles, precision versus the GPS, I mean, the first thing you want to do is to take this and like throw it, okay? Okay, sell it to the museum, right? Okay. So that, I mean, that could be one of the answers. But yeah, the thing is, everything is relative, everything in life, everything is relative, right? So let me see if you can see the globe from there. So you might think that that 2 miles is a very long distance, right? Okay, but it depends, right? So we're here, right? Can you see from there? We are somewhere here on the Keys, right? Any idea how many miles we have here to, let's say, Europe, Spain, just to say something? Any idea how many miles is this? 5,000? Anyone? 4,000. It's around 4,000, okay? Yeah, it's around 4,000, 4,100. Let's say 4,000, okay? So you have 4,000 miles. If you, with this, you can know your position within 2 miles, okay? Here in 4,000 miles, that's nothing, okay? So if you are here in the middle of the ocean, right? It doesn't matter if you are 2 miles to the north, west, south, okay? It's the same, okay? So, the only thing to know is pretty much where you are, okay? You don't need exact precision, okay? The idea with this is you need to know where you are. You are not going to use celestial navigation to enter a cruise ship in the Miami port in the middle of the night with a foggy night, okay? So it's not for that, okay? But at least it will help you to get you to the Miami port within 2 miles during the day. Then you stay there, and whatever is clear, and you can be visually, and then you enter the port, okay? All right, so you're not going to land the plane again in London in the middle of winter with this, okay? So forget it, all right? Or in New York, okay? So there's not for that, okay? But anyway, when you say 2 miles radius or 2 miles precision in the middle of the ocean, or here in the middle of the Pacific, which is even wider, okay, that's fine. That's what we need, okay? To have a general idea of where we are. That's what we need, all right? Okay. So again, if you think that that 2 miles is too much, yeah, it's too much compared to the precision you will need to drive around, your neighborhood. But to sail in the middle of the ocean, that's what you need, okay? Actually, 2 miles is pretty good, okay? All right. Any questions so far? Are we okay? Right. All right. Let's keep going. And as we said earlier, there are many techniques in celestial navigation. We are going to do the basic, which is the noon side, okay, because it's the simpler and the basic, because we don't have time to explain the other techniques, okay? This 2 mile precision, what we said, this 2 mile precision is pretty much with the other techniques. So tomorrow we might get a little more, because the noon side is the simplest one, or the easiest one, but it's the least precise as well, okay? But anyway, we're going to get, decent results, don't worry for that. All right. And as you can see, this is the little sextant, that they used to, that I still use, okay? That is an old picture, right? But this is when the sextant was the only way of knowing, where you were or where you are. And this, by the way, is a picture of World War II. This is like this is like a marine sextant or a classic sextant, which is like is this one, okay? And this is like called a navigation sextant or aircraft sextant that we use in World War II, okay? So this is a real picture or image from World War II, okay? That's the only way. Yes, go ahead.
Do pilots in the air have to have a backup just the way the sea captains do?
No, they used to do it. Until the 70s, they used to do it. But then they replaced, first what the progression was, first the GPS, then they started, first the sextants, yeah, then they started with the inertial systems, and then the GPS. The inertial system, probably if you never heard of that, inertial system is like a little magic box that have some inclinometers, accelerators, and gyroscopes and things like that. They can measure the movement of a vessel or a plane. Okay, so you have to calibrate it when you take off. Yeah, we are here at the Miami airport, this particular position, and then that little box will sense, your movement, and then they will track the position. Okay, they are very precise, by the way. Okay, that's what the modern planes uses. The American Airlines, United. That's what the submarine uses, by the way. And believe it or not, in all the planes that you fly, not the submarines and all the big carriers, the inertial system is the primary way of navigation, and then the GPS. Okay, so the GPS is second. Okay, believe it or not, right? And any idea why? The GPS wouldn't be the first source of navigation on the planes or on the ships. Any idea why? Right, the US government can say like this, okay, and then there's no more GPS, okay? Probably, if you read the news, you heard that over the Ukraine and now in the Middle East, there were some issues with commercial planes losing reference because the US shut down the GPS on a particular area. You can, right? You can shut down the GPS on a particular area just to make sure that the enemy doesn't use it, right? Okay? But if you are flying, or you are flying on, again, I say American Airlines, but it could be United, whatever, right? From Miami to Europe, okay? And the GPS stops in the middle of the ocean, what are you going to do, okay? So that's why inertial system is like a sole reference system, also an auto reference system that doesn't depend on any external source, okay? That's why first they use inertial system, then they use GPS, and on the planes they used to do the sextant, and on the vessels they use it in case, the inertial system, the GPS system doesn't work, all right? That's okay with your question?
No.
Okay, go ahead.
I found the terrestrial failure of GPS with coronal mass ejections.
Can you say louder because I can't hear from you?
Oh, I was saying the terrestrial failure of GPS is why the backup.
Right.
Because it could fail and
Right.
the coronal mass ejections.
Right.
take them.
Yeah. As far as I know,
You didn't mention that.
yeah, as far as I know, the GPS never failed. Okay, that's what they say. Okay, so it's difficult that GPS failed because they also have a lot of satellites as spare satellites and everything. So it's very difficult that GPS never failed in the last 3 years. But it can be interfered by the Russians or some of nice people over there, or can be shut down by the government. Okay, so so we have to be careful with that. Okay, that's why you always need to have a backup navigation system. In particular, you are in the middle of the ocean, right? So that's the thing, right?
The terrestrial?
It's called the inertial navigation. Inertial because it works by inertia. Okay, so all the accelerometers and the gyroscope and everything, they move the inertia. Inertia is, I mean, you know what inertia is, right? Okay, it's the resistance of something to move. Okay, so depending on the inertia, these gyroscopes and the accelerometers, how you measure. All right.
You didn't mention Loran. Loran was part of navigation history, isn't it?
Which one?
Closer to GPS.
Loran, yes. Loran was a terrestrial-based system which were out of radio. Okay, was like a Loran. The way that Loran used to work, they have like a different antennas on different on the coast, and they will transmit signals. And what they do is one signal like this, one signal like this, and they use triangulate. Okay, that's pretty much. It was a triangulation system. So imagine that you have a signal, a radio signal, right? Like transmitting from here, another one from here. Wherever they cross the signal is where you are. Okay, it was a kind of triangulation system. We can do well, at least 2 signals, or maybe 3. Yeah, I think they got to continue, but it was used until probably 10 years ago. Okay, so yeah, that's what I mean. It's not anti-history either. Okay. Yeah, no, it was. Yeah, but it had to be close, relatively close to the coast. Yeah, no. Yeah, but he's saying that he used it before, and there's sometimes interference. Yeah, sometimes it's not as easy, but it works. Yeah, of course. Yeah, that's another one. All right, let's keep going. Another time. Yeah, another time. Okay, let's talk about a little bit about the coordinates on celestial navigation. Okay, that's an important part. Okay, so for you that they are expert astronomers, I know that you know how to get coordinates of any celestial body, right? So if you want to find any celestial body, when I say celestial body, is the sun, the moon, the planets, and the stars. Okay, those are the things that we use in celestial navigation. And when I say the sun is only one, the moon is only one, the planets anything that you can see visually. Okay, so in celestial navigation we don't use any telescope or anything like that. Okay, whatever you can see by naked eye is what you want to measure. Okay, you might have like a little telescope over here, but it's going to be something small. Okay, but whatever body that we use is going to be something that you can see. Okay, with naked eye. Okay, so sun, moon, the planets, and the planets are not any planets, right? So what are the planets that we can see visually? Anyone knows?
Jupiter, Saturn, Mercury.
Okay, so from the closest to the one. So what's going to be the closest to the Venus? Well, we can see Mercury from time to time, but sometimes the problem with Mercury is, it's too close to the sun and it's not very available, right? So Mercury, we don't use it. We could, but we don't use it because it's difficult to find. So we use Venus. Then what follows after Venus? Mars. Well, the Earth, of course, Mars. Then Jupiter, and the next, Saturn. Can we see all those planets visually? Yeah, right? No, every night, every year, right? Every day, every night. But depending on the time, we can see them, right? Okay. Can we see Uranus? Naked eye, right? No. Neptune? Either, right? Okay, that's we only use Venus, Mars, Jupiter, and Saturn. Okay, those are the planets. And out of the stars, how many stars you can see visually here and every night, more or less naked eye? Okay. No, I know depending on where you are or whatever, yeah, but a number. What? Oh yeah, probably. Yeah, depending on where you are on the Earth, depending on the time of the year, right? But anyway, so in celestial navigation, of course, we don't use all the stars around. So we use only 57 stars that are the brightest stars at night. And of course, we cannot see the 57 stars every day, every night, right? Because that depends if you are in the northern hemisphere, you are in the southern hemisphere, if you are in winter, you are in summer, okay? But the list of stars that we use are 57, okay? Those are the ones that are studied and measured and everything just for celestial navigation, okay? Just for you to know, okay? So I think, and depending on where you are, depending on the time you are, and depending on where you are, is what star you want to use, right? Is that clear? Are we fine? Yeah? Are we okay? You're not falling asleep, but I'm there, right? No? Are you okay? No? All right. Okay. Well, let's see. And again, you guys are expert astronomers, no? Okay, so maybe one of the concepts that we talk about here, they are easy for you or they know them. But when you want to locate a celestial body, you need at least 2 references, right? That's correct? Right. One of the references that we use in astronomy is declination, right? Everyone knows what declination is for a star or whatever it is? Yeah. So the declination is no more like the angle of the whatever body, it could be the sun, it could be the moon and a star, to respect to the equator, right? Which is pretty much this angle, okay? That's what declination is. It's the same declination that you use in astronomy, okay? Same story, okay? That doesn't change, okay? Same story. Declination can be north or can be south, right? So declination is going to be always from 0 on the equator to 90 degrees, or from 0 to 90 degrees south, right? Are we okay with that? Who can tell me what declination Polaris has, more or less? Right, it's almost 90, right? Not 90, but it's almost 90, right? Why? Because it's up here, right? On top of the North Pole, okay? It's not exactly 90, but it's, let's say about 90, okay? Is 90 declination north or south? North, right? Perfect. The Southern Cross, okay, the name of our club, okay? So the Southern Cross, I mean, will be around here, right? So on the southern hemisphere, right? Is that correct? So the stars on the Southern Cross will be, will have northern declination or southern declination? Southern declination. Right? That's why, I mean, we need to get closer to the equator to see them, okay? Depending on what time of the year as well, right? All right? So declination is an easy concept, okay? So that's easy, okay? So I'm sure that you understand that. What is the other system that we use before we put it on the screen? The other measuring system that we use in astronomy to measure the other position?
Right ascension.
Which one? Right ascension. Okay, are we okay? Is right ascension? Everyone know what right ascension is? Yeah, right. So what's right ascension, by the way? Anyone can tell me?
Oh, it's an hour. It's based upon the hour, but 1 hour is about 15 degrees.
All right, but it's based, I mean, it's measured from where?
It's measured from where the equinox crosses the equator.
Right. Oh, what is, have you heard about the first point of Aries? Right, okay. So what we do in astronomy is, if we get the equator here, you know that the sun, I mean, goes around the Earth, okay, but it's actually the opposite, right? But I mean, just for this, the sun goes around the Earth, and now we are in, so if this is the equator, right? So the sun right now, right, is on the southern hemisphere or on the northern hemisphere? At this time of the year, right? Where? Okay, the sun at this time of the year is on the southern hemisphere, right? Okay. At what point the sun is going to be close, the maximum southern point? At what time or what day of the year? Okay, here are different things. You say winter solstice, and you say equinox. No.
Or the fall, which would be September.
Right, but that will be the equator. That's what we. Right, that will be the equator. But right now, the southern point is going to be on the winter solstice, which is December 21st, which is going to be on the Tropic of Capricorn, right? On March 21st, they will cross the equator, and when it crosses the equator is what we call the first point of Aries, and that's the point of reference for the right angle of ascension, right? That's what it is, okay? And then, I mean, the goal will continue going up, and what is the highest point that will go? Tropic of Cancer, and what day will be that? Around June 21st, depending what part of the year you are, but let's say June 21st, just not too complicated, right? All right. Well, in celestial navigation, yeah.
It's only half a degree that way.
Yeah. Okay, is that clear? That we are clear with that? Well, in celestial navigation, you know, we use a different reference for what will be longitude. Okay. So what we use here is what we call global hour angle. Okay. So the global hour angle is no more than the angle or the number of degrees from the Greenwich meridian, okay, over here to the right, okay? So you put it this way, the Greenwich meridian will be over here, right, on England, okay? So that will be the zero line, right? So the angle, the hour, global hour angle or Greenwich hour angle will be from here all the way like this, okay? And I go 360 degrees, all right? Okay, so it's not east or west, okay, like longitude. From here will be 0. So from here in Miami, we are pretty much 80 degrees. And if we continue going, we go all the way to 360, okay? So it's the same thing that right angle of association. Instead of being measured from here, from the first point of Aries, is measured from the prime meridian, which is the goal that goes the longitude 0, okay? So do you understand that? Is that clear? So let's go. Meridian, whatever go that way, will be the right angle, okay? So will be kind of a longitude, if you will, of any celestial body, okay? It's the same thing of, again, same thing of right angle of ascension. The only thing that is measured from Greenwich, and is measured in degrees. It's not measured in time, okay? The right angle of ascension is measured first in angle and then converted to time, okay? But it's the same thing, okay? At the end of the day, it's a different system of how to locate your celestial body, okay? The only difference is you measure from here instead of measure from the first port of Aries. Yeah. Same story, okay? But anyway, do you understand that? Okay, it's very simple, okay? So again, I mean, if you're in Greenwich, it will be 0. If you are some here, it's going to be 40 degrees. You're in Miami, it's going to be 80. If you're going to be like in California, it's going to be 130. And you go here in Japan, it's going to be probably around 230 or 40. Okay, again, it's just all the way around, okay? There's no east or west, okay? It's just one way, all right? Okay, so, and if you wonder how we get that information, we get it from the Nautical Almanac, okay? Have you ever heard about the Nautical Almanac? Yeah, all right. But the Nautical Almanac is a book that they used to, well, it's this one. It's just one page, okay? It's a book, I didn't bring it, but I bring it tomorrow. I have it in the tent. It's, I mean, it looks like complicated, like here, okay? But this is how the Nautical Almanac looks like, okay? So don't worry about this. I mean, it looks complicated. It is complicated, but it's easy to read, okay? So I know I can move to that side, so I'll try to do it to this side. Don't worry about too much about this. It's different between UT1 and UTC, okay? Don't worry about it for that. A couple of things. The Nautical Almanac, you need to, this is just the page for today, right? For today and tomorrow. Actually for tomorrow, because today is 5th, tomorrow and the next. In general, the page, every page covers 3 days, okay? 6, 7, and 9. I just put it here the first day, okay, which is the 6th. It's gonna be the day tomorrow. We're gonna use tomorrow. And then here you have a lot of information here, okay? So one of the things you can see here is the sun, the moon, okay? And then the second page of the stars and the planet, okay? I just put in this one because we're gonna use only the sun, but it's the same thing for that, okay? And the information that you need to read over here is all the time, well, first you need to make sure that you're using the right day. Second important thing here, you need to make sure that all the times here are UTC times, okay? UTC, Greenwich time, Zulu time, so you know what I call it, okay? Same thing, okay? This is no local time, this is UTC time or Greenwich time, okay? By the way, what is the difference between local time here now and the Greenwich time or the Zulu time? Anyone knows? 5 hours. Behind or ahead? Behind? Who says behind? Okay. Anyone thinks ahead? No? So why do you think we're behind if the Greenwich is here, right? So the Earth rotates this way, right? Rotate like to the east, right? So if we are here, I mean the sun is going to take 5 hours, let's say, to get here, right? So we are behind. All right? Okay. So what time is now right now? Because I have like 11:40, right? Local time. Okay. Anyone can tell me what will be the UTC time now? We need to learn if we are 5. Right. If we are 5 hours behind here, if we need to know the UTC time, we need to add 5 hours, right? Is that correct? All right. So what time will be? 4:40, right? So yeah, 4:40. All right. Remember that in Greenwich time they don't use AM or PM, right? They go from 0 to 24, it's like the military, right? So okay, so that's what you see here. Sorry, my producer for moving, but here you see go all the way from 0 to 23, right? Because here after 12 it doesn't start at 1 p.m., 2 p.m. Okay, it goes all the way from 0 to 24. All right. Okay. So what time you say it was in Greenwich time? 1640. I don't like it. Okay, that's all the military, right? So 1640. Okay. All right. So we should be around this one, right? Okay. So we should be here or here. Okay. This is the global hour angle. This is how many degrees the sun moved from Greenwich, at this time. Okay. Before.
What did GHA stand for?
It's a Greenwich hour angle. Okay. So before we do that, look at this. You see here, between 12 and 13, this is Greenwich time, right? Noon time. Look at the sun went from 3:56 to 11. So meaning that at some point it crosses 0, right? So between 12 and 13, it crosses 0 at some point, right? Because it went from 366, which is the maximum that can go. 356, and how much will be an entire circle? 360. Okay, so it means that at some point it crosses the Greenwich meridian, right, between 12 and 13. And then we'll see where, okay, in the next page we'll see it. But you can see here, it crosses at some point between the 12 and 13. Okay, is that clear? That's fine? All right, so what time we say was here? 1440, let's say 1440. So we're going to be somewhere here, right? Which means that the global angle of the sun will be between 56 and 71, okay? Which means then, let me go here, means, let me see, that the sun is going to be somewhere here. It was at 12, it crosses here, right? 12 UTC always, right? Now it's 1240, it's going to be around here, right? Yes? Does that make sense for you that the sun is here? I mean, in this position, more or less? Why? Say it again? Yes, but what else? Yeah. So what longitude we are here, more or less? Any idea what longitude we are here?
81 degrees.
Let's say 80 degrees, 81 degrees, okay? So if now the sun is between 56 and 71, that makes sense, right? It means because we are 81 degrees, right? So we are somewhere here, which means that this time the sun is probably closer to 70, say 65, 70, and that makes sense because we haven't had the solar noon yet, right? Okay, the solar hasn't crossed, you know, the north line south. All right, do you understand that? All right. So we said that we are at what longitude? 81. Okay, so we are going to be somewhere between here and here, right? So we are between these longitudes, right? Which means that the sun is going to cross our position at some point between 17 and 18 UTC. What time is going to be 17 UTC converted to local time? Oh, say it again? Say it again, noon, 12, right? So 17 minus 5, 12, right? So which means that the local sun or the local noon, okay, again, the local noon is when the sun crosses the north-south line, okay? It's going to be at some point between 17 and 18 UTC, okay? We are at 81, so it's going to be closer to 18. So it's going to be closer to 1 p.m. It's going to be 12:40 or something. Then we calculate that, okay? But you understand this concept, but you don't see it? Okay? So the first thing you want to know at what time is going to be noon in your location, first you have to have an idea of what longitude you are, more or less, okay? No exact. We say 80, 81 degrees. So we know that we fall between these two marks over here. So the local noon is going to be between 17 and 18 UTC, which is 12:01 local time. All right? Is that correct? Is that clear? Yeah, do you get that clear? Remember that when we change the time here now in March, I think it is we're going to be 4 hours behind, right? So the UTC is always the same, doesn't change. We're going to change the local time, okay? Instead of being 12:30, it's going to be 1:30. All right? Is that clear over here? Yeah, over clear? Okay. Ask me if you have any questions, because that's important, okay? So that's the way that we measure longitude of the position of the sun. Okay, going back. Okay, let me see if I can go back, if I can. And again, so declination is the angle between the equator, north to south. Global hour angle is how many degrees we move this way, all right? So quick question, how long does it take for the Earth to do like a one complete revolution? 24 hours, right? Yeah, it's not 24 hours, but let's say that's more complicated, but let's say 24 hours. Depending on where you measure against, right? On a star or the sun. But against the sun, let's say there's 24 hours, right? How many degrees do we have a complete circumference? How many degrees is that? 360. Okay, so how many degrees we move, does the sun move per hour then? 15, right? It's going to be 360 divided 24. Okay, you divide 3 24, which means that the sun moves like 15 degrees in longitude every hour. Is that correct? Yeah? Okay. So that's why, if you can see here, let me see, I'll go. No, this way. So let me show you the nautical almanac again, if I can. No, this way. Sorry. So let me see. You see here. You see here. How much is 26 minus 11? Oh. Sorry. I'm going to say on this one side. No, I know. Okay, look at this here. How many degrees take? I mean here. How many degrees is? How much is 56 minus 41? 15, approximately 15, right? Take 326 minus 311 is 15 as well, right? okay? As you can see, every hour the sun moves 15 degrees, okay? To the west in this case, right? Because that's the way it's measured, all right? So that's the other way you can see it over here, right? Okay? So let's keep moving. The other thing, the important thing here, sorry, is the declination, okay? Here, that's the information that you get. This is the declination of the sun hour by hour, okay? So we need to know what the declination is at this time. We said that it's going to be 4 something or 16 something. The declination is going to be south, 15 degrees and 38.8 minutes, right? And at noontime, it's going to be between these two times. It's going to be around, it's going to be somewhere in the middle. And we can interpolate this, okay? So we can do the math and interpolate this, okay? It's easy to get, okay? We are not doing it right now. We're doing it on Thursday when we do the math, but we can interpolate and know exactly the declination of the south or the sun, you know, tomorrow when we take the measure. Because when we take the measure, we're going to take time, hour, minute, and seconds, okay? We're trying to be as precise as we can, all right? All right, couple more things. Are we doing okay so far? Yeah? Yeah? You understand? You understand anything? Yeah.
The 2 dots have any significance in the declaration?
Say that again?
The 2 dots that have any significance in the declaration.
This one?
Yeah, what is that?
No, this means that 15 go all the way over here.
So those 2 dots don't mean anything.
No. Instead of putting 15, 15, 15, 15 here, they put it just to make it easy to read, okay? Instead of putting 15, 15, 15, 15, they put it this. So this means that 15 goes all the way, okay? All right. Question for the expert astronomers that we have here, okay? So any idea how fast the sun moves around the Earth in terms of miles per hour? How much?
Close to 1,000 miles.
1,000, right? So it doesn't look like it is difficult to see because we see the sun, but if the sun were just like a laser point, if we move like 1,000 miles an hour on the Earth, right? That's fast, okay? That's a lot of fast, okay? Which means that it moves 1 mile every 4 seconds, okay? 1, 2, 3, 4. The sun moves over the sky 1 mile, okay? Which is fast, okay? Okay? Which means that we need to be very precise when they take the times, because a 4-second difference on the time that we take, or a 4-second error, if you will give us an error of 1 mile, okay? So that's why we need to be very precise on what we measure, okay? So it's not that we take what time it is, more or less 48, something. No. Have to be, you know, as exact as we can, okay? Because again, 4 seconds difference is 1 mile error, okay? So that's why? Because the sun moves that fast, okay? You know how much, so the sun, how much does it take for the sun to cross Florida from the east to the west coast, more or less, any idea? How much would it take? No, it's a minute and a half. 1 minute and a half, okay? Yeah. So from the time that the sun is right on the east coast, right? 1 minute and a half later, it's going to be on the west coast, okay? It'll go from Miami to Naples, let's say, in 1 minute and a half, okay? That's fast, okay? All right? So it doesn't look like, okay, you see, oh, the sun is over there, okay, it doesn't move, but it moves fast, okay? So that's why we need to get precise, all right? Is that correct? That's fine? Yeah.
When you're talking about the sun moving, actually it's the Earth moving.
No, right,
It's
yeah.
the Earth moving.
No,
I don't mean to correct you.
No, you're right. No, if our friend Copernicus listens what I'm saying, he's going to kill me. Okay? So, why you guys, the sun is the one. No, I know. For celestial navigation purposes, let's say that the sun is the one that moves around the Earth. Okay, so we all know that's the Earth. Okay, no, that's fine.
Galileo straightened that out for us.
Yeah, no, that's clear. No, that part I learned. Okay, trust me, I know. But I mean, for these purposes, I mean, believe it or not, the Earth is the center of the universe for celestial navigation. Okay?
Right, exactly.
Yeah. Which is not a bad thing, you know. From time to time, it's not a bad thing, you know. Anyway, all right, no, you are right. Okay, you're right. So anyone understand what this means? Okay, more as an idea and what declination means. Same thing for the moon. Okay, there's a couple. These are like some correction that we need to do later, but don't worry for that. Same thing for the moon, and if you see the nautical almanac for the stars is the same, and for the planets is the same. Okay, so in a production, an effort of production, okay, we brought all this. So I had many copies, but just pass it around. At least one have a couple per table, so you can see it closer. Okay, just one per table, and then if there are more, we know. Okay, but share it in the table, you can see it. So that's the same thing that you see over here, right? Okay. So anyway, don't look at that too much now. So pay attention to me for now, okay? And then we'll do it later. Yes, but you can take it home, and then make sure that you bring it on Thursday, okay? Because we are need to do the math, okay? But that's the nautical almanac, the entire page. Just one more thing of the nautical almanac, if I can. Sorry, but okay, but this is what we talk about the time. Okay, so we already discussed that. Let me show you just one more thing in the nautical almanac. Okay.
Can you interpolate those various ledgers on that chart?
Say it again. I'm sorry.
Can you interpolate between those two numbers?
Yeah, you can interpole. Yeah, of course. Yeah, because we know it moved 15 degrees, so you can interpole between the time. Okay, so yeah, you can. Actually, we had to. Okay, all right, all right. Well, a couple of things here. Okay, yeah, go ahead.
One question, what does the HP stand for in the
That's called horizontal parallax, which is one of the errors that we need to consider when we measure the moon. Okay, that's called horizontal parallax. Okay, and I explained that's on Thursday. Okay, we're not gonna use it because we wanna use the sun, but that's what it's called, horizontal parallax. Okay. Then I mean, after if you want, after when we finish, we can get together and explain the details of what it means. Okay. Right. All right. Well, as we said before, I mean, it is clear that the Earth is the one that orbits around the sun, right? Do we agree on that? Yeah. Copernicus, Galileo, and company, they say that that's correct, right? Yeah, that's what they said. Okay. But a couple of things. Okay, interesting thing. I'm sure that you know it. Okay, but I mean, let's refresh it. Okay. So the issue with this, I mean, the issue, and then that's we have the declination that we have all the seasons and everything. Okay, we're not going to explain all that. I'm sure you already know it. But the issue with this is the Earth does this orbit around the sun. Is a circle? Is a perfect circle or not? No, right? It's not a circle, right? It's more closer to an ellipse, right? Let me close on this way, right? It's more like an ellipse, right? Or the mathematician will say an ellipsoid, okay, which is more complicated, okay? But it's not perfect, right? So which means, okay, that the distance between from the sun and the Earth is not always the same, right? So it is closer at this time of the year in December, and it's the farthest in June, right? We agree on that? Do we know that? Oh, do you know that? Yeah, that's clear. Nothing new, right? Okay. All right. So a couple of things. The orbit of the Earth is an ellipse, right? Which means, again, the Earth is farther closer in December, closer and farther, and it's pretty much at the same distance during the equinox, right? September and March. Okay. So and that's part, probably that's part, I mean, do you know that? I mean, that the speed of the Earth orbit is not the same, okay? So the speed, I mean, this is the orbit, right, of the Earth, right? Since this is not an sphere, okay, it's an ellipse, okay, the gravitation force of the sun against the Earth is not constant, okay? When it gets closer, it gets more gravity, more attraction, and when it farther, it gets less, okay? So because of that, and because of what is called the second law of Kepler, the speed is not always the same. Okay, so this part is faster and the part is slower. Okay, so which means that the speed that the Earth orbits around the Earth is not constant; it changes. Okay, during the year. Yeah? So it doesn't change much. Okay, but it changes. Okay, because this is an ellipse. Okay, if it were a perfect circle, it would be the same speed at the same time of the year. Okay. You might wonder, I mean, why we need that information? Because depending on the speed, the sun is not going to cross the Greenwich meridian at the same time every day. Okay, let me show you. So because of that, there's something called the equation of time. Probably you heard of this. Okay, the equation. I'm going to move to this side. Sorry for my producer. The equation of time means how many minutes the sun is going to cross the Greenwich meridian, either behind or ahead, okay? Which means that when the sun is moving slower around the Earth, they're going to be, it could be until like almost 15, 16 minutes slower. It's going to cross any meridian, but the Greenwich meridian on February right now, let's say, is going to cross around 12, 13 minutes before. Okay, I'm sorry, later. Okay, no, before, later, and at this point in October, November, it's going to cross the equator. Okay, 18 minutes later, which means that the sun, I'm going to see now in the almanac, in February is not going to cross the Greenwich meridian exactly at 12. It's going to cross a few minutes later because it's behind, right? It's slower. Okay, and here it's faster. Okay, so we need to take it into consideration because we are taking Greenwich as a reference, right? And we are thinking that the sun is going to cross Greenwich exactly at 12. which is not the same. Only a few times a year, like here, 1, 2, 3, 4 times a year, the sun is going to cross the Greenwich meridian, our reference, exactly at 12. Okay, so when we measure the time, or here at what time it crosses our local meridian, we need to know at what time it really crosses Greenwich, because otherwise we are calculating the time wrongly, right? Okay, do you understand that concept? Right? Probably you knew this, okay, but I mean, it's always good to refresh it. Okay, so if you wonder where this is called equation of time, and then if we go to the nautical almanac now, okay, on the page you have, you see on the right side. Let me show you something. I'm gonna take this for a second, okay? If you see, look at the page you have over here, this part, okay? That's the equation of time over here, okay? Yes, you can see over here. If you see that part, this is the equation of time, okay? For this particular date, okay? Because the equation of time, as we saw, changes, right? Changes all this, okay? Right? We said that we are in February, let's say beginning of February, the equation of time, the sun is slower, around, let's say, maybe for 13, 14 minutes. You see here, the day tomorrow, this is for tomorrow because tomorrow we take the size, but you can go to today's day, is the same, right? So it says that today or tomorrow in this case, the equation of time is going to be 14 minutes, okay, which matches with this, right? Around 14 minutes, okay? But it's going to be slower, okay? What that means is the sun is going to cross the Greenwich meridian tomorrow at 12:14 Greenwich time or UTC time, okay? It's not going to be at 12, it's going to be 14 minutes later. Why? Because of the different speed of the sun that we talked about yesterday, okay? And that's important because we need to take this into reference when we do the math on Thursday, okay? If you assume that it crosses at 12, it's going to give you 14 minutes difference, okay? And that's a lot of time, right? A lot of distance as well, right? Okay, is that clear? Do you understand that? Okay, so that's important. Okay, that's important to know. Okay, and if you look at the nautical almanac, you will see there are times that this is 0 pretty much, and sometimes it's negative. Sometimes maybe 11 when you go like this part, when the sun is faster, like almost 18 minutes. So the time that it crosses might be 11:40, 11:45. Okay, meaning that the sun will cross Greenwich 15 minutes before noontime, before 12, okay? That's an important consideration that we need to know, all right? Right, because what we are going to do tomorrow, tomorrow, Thursday, we are going to measure the time that the sun crosses the meridian. We're going to see the time, and then we are going to make the math of the difference between the time and the 12, but not the 12, the 12:14. That's going to be the real time, okay? Okay? Yeah, go ahead.
Why doesn't the nautical almanac automatically make these changes, given that they're both date related?
Because this depends on every day, right? This moves like the equation of time, right? So you need this changes every day according to the equation of time. Okay, right? Yeah, this is no more than a representation of this curve. Okay, like a little more exact to every day, right? Okay, is that clear? That's fine. Are we okay? All right. Couple more concepts. Okay, so we are closer. Okay, so don't worry, it's not going to get more complicated than this. Okay. All right, couple more things. Do we know that the sun path along the ecliptic, right? Everyone know what the ecliptic is, right? So we know that part, okay? So we explain, expert astronomer, we don't know what it is. Okay, if you look south in this case, okay, because we are in the northern hemisphere, okay, we are here on the northern hemisphere, we agree that the sun is somewhere here, right, on the south, right? Okay, because the inclination is south, it's going to get on the equator on March 21st, and it's going to go north. So, which means that in this point, if you want to see the sun path, we need to look south, okay? Right? Do we agree on that? And if we were on the southern hemisphere, we have to look north, okay? Right? Okay? All right. So the path of the sun along the ecliptic is something like this, right? You assume that this is like looking south. The sun will, the sunrise will be somewhere on the east. It's going to be like a noontime. It's going to be sunset. It's going to be sometime on the west, okay? Is it exactly on the west and the east, or there are some differences? So does the sun really shows up, let's say, from the east, or there are some variation? Anyone knows? Variations. Okay, depend. What are the times of the year where the sun rises exactly from the east and settles exactly on the west? What was you saying? equinox, you say? Anyone else? It's only at the equinox, okay? And March 21st or September 21st is the only times of the year anywhere in the earth that the sun will rises on the east, exactly on the east, right? Exactly 90 degrees, and will set exactly west, okay? The rest of the year, in winter time, will tend to, let's put it this way, in winter time, they will go south, okay? So it's gonna be more than east, and then it's gonna go more than south, okay? North, southeast or southwest, all right? But let's not complicate it, okay? Do we agree that the sun follows something like this, okay? Well, the issue with this, the sun will continue rising, but it will get to the point at noontime, no at noon this one, right? At noontime, okay, when it crosses the meridian, that the sun pretty much will be like a flat line like this, okay? So the altitude of the sun will start stabilizing like this, and we get to a point at noontime that pretty much the altitude of the sun versus the horizon, which we're gonna measure, is pretty much stable, okay? You see it's pretty much zero. Not zero, it's gonna pretty much stable, okay? So here we'll go up quickly, we'll slow down, and then we'll start, accelerate again, okay? So what we want to do is this. This is called the survival method, okay? But it's the same thing that we're gonna do tomorrow. So what we're gonna do with this is, first, we're gonna try to measure the time when the sun gets to the maximum, right? Which is gonna be the solar noon, okay? Which, by the way, is gonna be difficult to measure, okay? Why? Because the altitude here varies very little, okay? You will see tomorrow with the sextant. So it's very difficult to see if the sun is on this side, before noon, solar noon, or after solar noon, because the angle, this altitude is nothing, okay? The variation is very, very difficult to measure with the sextant, at least with a regular sextant, okay? So to get this point with the sextant is gonna be very difficult. We try, but you see here you measure 30 degrees, 30.1, 13.2, 30.1, 32. It's very difficult to measure, okay? We'll try to do it, but you see that it's very difficult. That's why this method is not very exact, because it's very difficult to determine exactly when the sun crosses the northern line, okay? We'll try, and that's why we're gonna...
Sticks, right?
Yeah, that's why we use the sticks, okay? All right? Because when we have this, these simple sticks, you put it like this. What you're gonna do this, again on the ground, like this, and this with the compass, or with a cell phone if you will, okay, will orientate this, okay, exactly north-south, okay? And when the shadow of this is exactly this, they will mean that the sun will crosses the local meridian, okay? Yeah?
That is
Exactly.
lined up.
Yeah, so because the shadow, let's say that the sun is that way, right? So the shadow is gonna be this way. Before noontime, the shadow is gonna be this one. The shadow will start moving like this. We'll set exactly on this at noontime, and they will start moving that way. Okay, is that clear? Okay, it's difficult also to orientate this exactly north-south. Okay, because the compass has arrows and everything. But that's the idea. Okay, that's what you need. Okay, so we'll do it two ways. We'll do it this way, and we'll do it with the sextant. We'll measure the altitudes and try to determine at what time it is. Remember that we said that the sun moves like this. How fast we said that it moves? How many miles an hour? We said like 1,000 miles, right? So which means that every 4 seconds will move like a mile, right? So every 4 seconds the arrow will be 1 mile, okay? That's why with this system it's kind of difficult to get the exact longitude. So we try with this and we try with this, okay? And you see that pretty much works, okay? It might be a few miles difference, but you see that it works.
Cheaper than a sextant.
No, sextant is $300. No, this one, by the way, it's like $300. So it's a plastic sextant. Okay? A good one is like a $2,000, a metal one, bronze one. This one is $300. Okay. Is that clear? This part? Okay, we're clear. Let me show you a couple more concepts. So we are going to get again the maximum altitude with the sextant, and we're going to get this. The other thing that we're going to do, by the way, if you don't have a sextant, which might happen, I'm sure that most of you don't have a sextant. The other way of measuring this altitude will be by doing trigonometry, okay? Don't worry, it's something simple, okay? So that's the other thing that we're gonna do. Let me show you something before. Have you ever heard about magnetic declination? Any idea what it is? Okay. You know that we have the true north, or the geographical north, and then we have the magnetic north, right? And the true north and the magnetic north in general they are not in the same position, right? So these are all the declination lines, or it's called variation. I don't know what they say declination, but the real term is variation. This is how many degrees is the difference between the true north and magnetic north. You see here where the south magnetic pole is. The real magnetic pole, the geographic south pole should be around here, right? Should be around here. The real magnetic is on here. You see the difference? And the north is the same thing, right? It's in the same position. That's why we have all this, right? But if let's take a closer look at North America, just to make it simpler. If you see here, we are over here, right? Around here, right? You see the magnetic declination or variation actually is 5 degrees, meaning that the magnetic north is 5 degrees to the west of where we are, okay? So if you do like this, this is the true north that we are getting with the GPS or the phone. The magnetic north is going to be like this, okay? It's 5 degrees to the west. So if we want to use the compass, we need to compensate those 5 degrees, okay? Because the magnetic compass measures against the magnetic north, okay? And the GPS or the phone application measure against this one. If we do with the compass, you do with the compass, we need to compensate with that. 5 degrees is not too much, okay? It's difficult to measure 5 degrees with the compass. But if you go to places like, let me show you. Places like here is 15 degrees. You go to Seattle, might be 20 degrees, okay? Depending on what part of the world you are, the magnetic declination or variation might be significant enough that you have to adjust it, okay? So here, this line over here, the green one, is the line where the difference is 0. Here, if you are somewhere on this line, let's say on here, the compass will pretty much indicate the true north, okay? And again, depending on what part you are, okay? See, 10 degrees, 15 degrees, 15 degrees, 20 degrees, okay? Here is around 5 degrees to the west, okay? Tomorrow we'll try to compensate for that again. It's not critical, but if you can compensate by that, I mean, let's do it, okay? Because again, we are trying to get, when we do this, we're trying to get the true north-south, okay? Right, forget about the magnetic only for the compass, all right? Is that clear? Are we clear with that? Yeah.
When you say the magnetic one, then, is that the one that the compass would
The
point
compass.
to?
Yeah, the compass is the magnetic one. The true north is the real true north. So this is the true north, okay? The magnetic north might be over here, right? So it's not the magnetic north is right on the north pole. So that's why we have this magnetic variation. That's why we need to compensate. And these lines will tell you how much you need to compensate, all right? Okay? So, hold on, let's start here. I want to get there. Yes. No, the phone will give you a true north, unless you set it up as magnetic. You can as well, but in theory, the phone will give you true north. Okay, but you can set it up as magnetic as well. Someone have a question? What else?
Grid, there's also grid north.
What?
Grid,
What is that?
on the map. There's north and
Ah, the grid north. Yeah, no, that's true, but that's the difference between true and magnetic. Yeah.
that needs to be taken, there's actually two norths.
Right. Yep. No, you're right. Yeah. I don't want to complicate it here because we are not sailing, but yeah, you're right. No, you're right. Any other question? I think I heard a question. Yeah. For move, right? That's why it is from 220. Okay. So now we need to take. Yeah. But it doesn't change too much. Okay. So the maps actually will tell you how many minutes changes a year. I got this because that's the latest one I could find. Okay. But I mean, in theory, we could take like a 224. Actually, the declination flow is moving west. Okay, so right now instead of before might be 4.5. Okay, again for the precision that we calculate with this is the same, right? But again, yes, it moves, right? And it doesn't move to the west. Sometimes move to the west and move to the east. Okay, so it changes. Any other questions? Sorry, no. Are we okay? All right.
The iPhone uses magnetic north.
The iPhone might give you magnetic or true, both,
How do you know?
Yeah.
because you can set it.
Oh, you can
Yeah,
change it.
you can set it. I don't have an iPhone. I have like a regular Android. But the one that I have, that you can set it magnetic or true. Actually, the GPSs, if you have a portable GPS, you can set up the GPS to put it true north or magnetic north as well. Okay. If you are anywhere on the land, you want to use true. But if you are sailing and you're on compass, you need to set it up on magnetic. Okay. Same thing on the planes. All right.
They use magnetic?
They say use magnetic. But then the GPS will convert it to true. Okay. Go ahead.
NOAA has a magnetic field calculator.
Yeah, I know.
ngdc.noaa.gov.
Yeah, but don't get too complicated for that, okay? Because for the precision that we need to do, 1 degree more or less, same story, okay?
So they don't have to do that math up there, that just does it for them, and it shows up on a screen.
Yeah, and the GPS you can do it as well, okay? All right, so a couple more minutes just to finish. Let's talk about the sextants just to finish. The sextant is this like a instrument over here that moves like this. Tomorrow we use it tomorrow, right? The only thing that you do, you look through this, and what it does is you look through this. No, let me use this one. You look through this, and then the sun in this case will reflect like this here and here. Okay. So at the end of the day, what you see with the sextant is something like this. You will see the horizon, you will see the sun. Okay. The only thing that you need to do is to move this part over here. Okay, until the sun touches exactly the horizon. And then we go here and we measure the angle. Okay, that's pretty much what we need to do. Okay, that's all the thing that a sextant does. Okay, is to measure again the angle between our zero is going to be at the horizon, right? The only sextant that we need to do is to measure this angle. Okay, it's just a protractor. Okay, so by doing like what is called a double reflection, the sunlight will reflect on this mirror first, which is this one. Okay, then we'll reflect on the second mirror, which is this one, and then you will see through. And of course, we need to use some filters here, okay, not to damage our eyes, okay? In particular, when we use the sun, right? With the moon and the rest, we don't need it, but for this, it's important, okay? And these are some filters as well, just to cover our eyes from the horizon where there's a lot of reflection, okay? But the only thing it does is reflect the light here, here, and here, and you will see like a double image. You will see the horizon, and you will see the sun. And the only thing that we need to do, by moving this part over here, like this, the sun, you will see that the sun goes up and down. The only thing we need to do is to put what's called the lower limb on the sun against the horizon. That's what we need to do.
And then that's your number.
And that's the number. That's the number that we read over here. Okay? That's the only thing we need to do, okay? Don't get intimidated by this, looks complicated, but it's just a protractor, okay? All right? So let me explain to you a couple of things that we are going to need tomorrow, and when that we finish. This is what we're going to try to do with the sextant, right? So there's going to be one mirror, one part of the mirror. I mean, then I'll pass you through, right? But I mean, one part of the mirror, you will see the horizon. The other part of the mirror, you will see the sun like this. What we need to achieve is this, okay? Just to move the sun until it touches the horizon. The horizon is the water, okay? That's the best horizon we can get, okay? Right? And the only thing that we need to do as well is to make sure that we take the sides, we do like this, okay? We move the sextant like this, a little bit, okay? Just to make sure that the sun is in this position, okay? Because if the sextant we do a position like this, the sun is going to be here and this is going to be the wrong altitude, okay? So we need to balance it like a little bit, like this, until you see that the sun is right in the middle, okay? And then with this, you move a little bit until it touches the sun, okay? That's the only thing we need to do. We'll practice it tomorrow, okay? So don't worry. Sounds complicated, but it's not, okay? We need to practice on that.
So it doesn't necessarily always touch the
No,
horizon.
no, no. This
You
is
have to elevate it or
all right. First, you need to elevate it a little bit until it's in the center, and then you touch it, and you move it until it gets this. Okay. So first thing you do like this, as it's in the center, and then you move it. First with this, and then with fine tune like this, until you get it over here. Okay. That's what we need to do. Okay. And we will take like several sides, and then we'll try to do like an average or something. All right. Is that clear so far? Right? It's okay. And let me see if we got something else for today. The last part. Let me explain you how to read the sextants, okay? That's the most important part, okay? This is just a picture of this one, okay? Right? So, you know what, just we are going to measure degrees and minutes, right? So angles are measured in degrees, minutes, and what else? Seconds. Okay, in celestial navigation, forget the seconds, okay? We use seconds. We only use degrees and minutes and decimal of minutes, okay? So it's going to be, for example, I'm going to give example for example, 32 minutes, 32 degrees, 21.4 minutes. Okay, forget the seconds. Okay, we don't measure seconds on celestial navigation. So just to finish today, let me explain how to measure this. This scale over here, okay, is just to measure degrees, and this over here is to measure minutes. Okay, so we're going to run a couple of examples. Okay, how many degrees do we have here? That? Here's 20, right? 20, 21, 22. So it's between 22 and 23, right? Do we agree on that? Again, 20, 21, 22, 23. So the side is somewhere between 20 and 22 and 23. Okay? So the degrees is the entire part, right? Which is 22. Okay? That's fine? Is that okay? Okay. Now go to this part. This is the minutes part. You see this part over here, okay? This is our zero, let's say, right? So how many minutes? 15, 20, 21, 22,
And a half.
22. It's between 22 and 23, right? You see that? So the part you need a decimal is with this part. If you here, there is one line that's going to match any one of these lines. In this case, probably it's this one, okay? Which is 0, 2, 4, 6, 8, 10. So it's going to be 22.4. Okay, you get that? Again?
Oh, yeah, because it lines up with that.
Yeah, it's going to be always one of these lines that's going to line up, okay? This one doesn't line up, this one is one. Well, the closer one is this one, okay? Which is number, number 0, you go from 2, 0, 2, 4. Okay, this is 21, 22, 20, I'm sorry, 21, 22.4. Okay, you get that? You read that? That's what you measure, okay? Let's see another example. If we can, okay? Let's see this example, okay? And I took it randomly, just put it the sextant like this, and where it fell, okay? So how many degrees here? Let's see, let's do it, I mean, just okay. So 50, 55, 56, 57, right? Oh, we agree? 57 degrees. It's going to be somewhere between 57 and 58, right? So the degrees is 57. So here is how many minutes? 35, 36, 7, 38, 39, right? It's going to be 39. And how many, where's going to be the decimal? Probably this one, right? Yeah? This is the one that is touching this part, right?
32.
Yeah, so it's going to be 39.6, 0.8, I'm sorry. You read it?
Where the lines.
Right. Yeah, let me go this way.
I get it.
Yeah, let me go there. Let's do it again. This part is fine, right? So 40, we take, this is the 0, right? There's one over here. This is the 0. So the 0 is 36, 37, 38, 39. Okay, it's over 30, let me see.
Wouldn't it be 38.9?
Right, 38, yeah, it looks like 38. It's going to be probably 36, 7, 8. It's going to be almost 39, right? It's going to be 30, 38. And then what's the decimal? The one that it touches is probably this one, the closest, okay? Because this is far, this is far, this is touches, and this is far. So it's going to be 38.8. Okay, get that? Again, 36, 37, 38. The decimal is going to be is 38.8.
Oh, I get it.
Okay? You understand how you read? Okay? It's very easy, okay? So with practice, I mean, it's easy to do it, okay? Right? Do we agree on that? Any question on that? Then I'm going to pass the sextant around. You can play with that, okay? Do you have any question on that? No? All right? Okay. But that was all for today, okay? So don't worry. I don't think that's the one. What else? But we talked about this already. Let me see if there's something else. Yep, that's pretty much where it is, okay? So that was the theory for today. You have the nautical almanac. Take it with you. Okay, bring it on before you go. Don't go yet. Don't go yet. Bring it tomorrow. Tomorrow we're gonna meet here, same time, same place, same channel. Okay, here. Yeah, but tomorrow, not same time. Tomorrow is gonna be at 12. Okay, 12 local time. Why tomorrow at 12? Because at 12:40 is gonna be the noon side. Okay, that's why tomorrow we'll do it at 12. Okay.
And we have a break for a few minutes before the next lecture.
Right, so tomorrow at 12 here, let's meet here, and then from there we walk to the place, all right?
Bathrooms are right nearby. Thank you.
See you tomorrow.